Hello, pre-calc and trig students. We are here to talk about vectors. And what we're going to look at in this video is really just some of the basic things we need to know about vectors as we're getting started with them before we do anything really too involved. Starting with the most obvious question, what on earth is a vector? Well, a vector is a very useful tool for describing things that have some sort of quantity, some sort of value, and also some sort of direction. We use them to talk about force. We use them a lot in physics. We use them to talk about things like airspeed. And basically, you can think of it as almost like a cross between a ray and a segment to think in geometry terms. Remember back in geometry, a ray was like a piece of a line that had an end point or an initial point, but then when it went forever in the direction of some other point, and it passed through that point and kept going forever. As opposed to that, a segment just has two endpoints, and that's it. There's no direction of a segment, okay? So a ray has a direction, segment doesn't have a direction. On the other hand, a segment has a finite length, whereas a ray keeps going on forever. If you kind of put the two together, you've got a vector. A vector goes from a starting point to a stopping point. It has a finite length, and we very often use that particular length. The length, whatever the length is, represents a certain quantity associated with our problem. It could represent a force. It could represent a weight. It could represent a wind speed. So the finite length represents something, and then it also has direction. We know which direction the wind is blowing or which direction you are pushing a force or something like that. So it always has a starting point, which we call the initial point, and it has an ending point, which we call the terminal point. Think of the terminator. Something that is terminated is ended. So that is a vector. It's not a ray, because rays keep going on forever, and a vector does not. It has a specific ending point. It's not a segment, because a segment doesn't have any particular direction, whereas a vector does. And there are different ways we can describe that direction. Another thing we can use to describe with vectors is translations in geometry. If you want to translate a figure up and to the right, you can show how far and in which direction you want to go by a vector. So vectors are really very useful. Now, when are they equal? Vectors are equal if they have the same length and the same direction. Okay, so those are the two things you're looking for to know if vectors are equal. And very often when we say length, really with a vector, we don't say length, we say magnitude. It's size, it's magnitude. Now, let's look at how vectors are sometimes given to us. Now this says let v be the vector from initial point p sub 1, which is at -6, -3, to terminal point p sub 2, which is at 8, 5. Write v in terms of I and j. A couple things I want to point out to you. Vectors are very often named by letters u or v or w. They're also very often, they can be written sort of, notice I made my v kind of fancy. They're usually written as a script letter, meaning kind of like an italicized letter, or they can also be given this little symbol over the top. So different notations exist, and you just need to basically figure out what your book or your teacher wants to use. Now, this particular problem, I'm giving my starting point, my initial point, and my ending point, my terminal point. And I'm asked to describe this vector. There's a couple of ways I can do that. This one, specifically write v in terms of I and j, we're going to come back to. But let's look at it let's look at it in the graph. From x is -6, let me just sort of sketch this graph. That was not the most vertical of y-axes. But -6, -3, and it's rough sketching time here, to 8, 5, okay? 8, 5. All right, so let's talk about the horizontal and the vertical components here. Horizontally, this moves from left to right, because remember this was our starting point, starts at -6 down here and goes over to 8. So in terms of the x difference, it goes from -6 to 8. It goes 6 plus 8 to the right, which is 14. We could find that by doing 8 minus a -6. So 8 minus a -6 gives me 14, and that's my horizontal change here. Vertically, it goes from -3 up to 5, and sorry, my cat is walking right past the camera, so I hope you enjoyed his back. And that's my horizontal component. And vertically, from -3 up to 5, 5 minus a -3. So basically, on both of these, I'm taking the ending point and subtracting the beginning. But I'm doing it separately for the horizontal and for the vertical components. And I'm going to write this in what's called component form, which is basically I just take those two numbers and I do this. And these are not parentheses. They're almost like greater than, less than symbols. They're like specifically pointed. So this is called component form. This is one way of writing a vector. It's really my favorite form, honestly. But that's not how we've been asked to write it. We've been asked to write it in terms of I and j. So same vector, I'm going to write it in terms of I and j. And what that means is those are, another way of saying that, let's put it that way, is as a product of unit vectors. A unit vector is a vector that has a length of 1 unit. Specifically, I and j are ones that we tend to come back to and use time and time again. And we think of I as being a 1 unit long vector that is horizontal, and j as a 1 unit long vector that is vertical. Well, that happens sometimes. So basically, they're just saying break this into the horizontal and vertical components and write it as how many times do I do 1 unit horizontally and how many times do I do 1 unit vertically. So that would be just 14i plus 8j. It's really just the same thing. You put your horizontal component in front of I and your vertical component in front of j. So this is as a product of unit vectors is how we've written that. Sometimes it'll say as a product of unit vectors I and j. Now, not every unit vector has to be pointing directly horizontally or vertically. There's also, you could have a unit vector that points in any direction. And there's a way to find unit vectors that point in the same direction as your vector that we're not going to get into because on this particular video. There are quite a lot of good videos out there. If you want to say writing just Google writing a unit vector, you'll find plenty. So now the other thing I want to look at here is how long is this segment, or how long is this vector really, excuse me. So I wrote right through the middle of it, but basically there's my vector. And so if I want to know how long it is, I'm going to do the same thing I would do if I wanted to know how long that segment was. I'm going to use the distance formula or Pythagorean theorem. Well, we can already look at these components. We've already got it broken down into how far is this horizontally. Well, horizontally, we know it's 14 units. And how far is it vertically? We already know it's 8 units. So if we have it written either in component form or as a product of unit vectors, then we know the horizontal distance and the vertical distance. So we're going to use Pythagorean theorem. So if I want the magnitude of this particular vector, which means just basically its length, I'm going to do square root of 14 squared plus 8 squared. 14 squared is 196, 8 squared is 64. Put my calculator away here. That should be 260. So I've got square root of 260. I don't know off the top of my head if that simplifies. Let me looking at that. I think the biggest thing that goes into there is 4. So that's going to be, excuse me, 2 root 65. That's an exact form. You could also possibly change it to a decimal depending on what you're asked for. So now let's look at the magnitude the notation for magnitude, because I just said let's find the magnitude. How could I be asked to find the magnitude? Well, basically, if I want the magnitude of a vector, it's almost like absolute value symbols, but they're doubled. You have two vertical lines on either side of it. So for instance, in this particular problem, we were told that this vector was vector v. So one way I could have asked for the magnitude is I could say that. Okay, another way is it was in component form. I could say this. Or I could say as a product of unit vectors, I could have it written like this. All of those would just be saying to do exactly what we did here, just like the Pythagorean theorem, basically. Horizontal component squared plus vertical component squared, and take the square root. All right, so here's another one. Let's figure out what the magnitude of, let's call it vector mn. Let's say we want vector mn. So the vector that goes from m to n. All right, so its magnitude would be horizontal distance squared plus vertical distance squared. The horizontal distance here from -3 to 1 is 4. From 1 to 4 is 3. So this is a nice Pythagorean triple. This is going to be 5. At the same time, I also just found the component form of mn. Now, keep in mind, we have to think about which direction it's going. This is going left 4 and up 3. So that's -4, +3. And the magnitude of mn is 5. Okay, last but not least, we're going to manipulate some vectors because sometimes that's something we're asked to do. We've got 3 different vectors here. They're all written as a product of unit vectors or a sum of unit vectors. And we want to do various things with it. The first thing I want to do here is talk about multiplying by a scalar. A scalar basically means something that scales it. In other words, scaling it up or scaling it down, making something 3 times as large or half as large. So if I write, for instance, this, then I'm trying to take the entire vector u and make it 5 times as large. So I just take each component and multiply it times 5. So that's now -10i plus 25j. To me, it's a little bit easier to see this when we think about it in component form. So I'm going to take each of these and think about it in component form. And those are the component forms of those vectors. So now I can not only do scalars, but I can also add and subtract them. So let's say I have 3u minus 4v. Okay? So that means I'm going to take 3 times the vector u minus 4 times the vector v. My biggest advice to you about these is really to just go ahead and don't mind wasting the paper. In other words, don't try to do it all in your head because you will make a mistake that could be very easily avoided by writing it out. So I would probably take the time to go ahead and write, to multiply 3 times, do every step. 3 times -2, 3 times 5, and then 4 times 3, 4 times -4. Be careful about this minus and what you do with it here. If I had wanted to, I could treat it as a -4 instead with a plus. In other words, this is plus -4. And then I'd have -4 times 3, and I'd have -12 here. But you don't want to do it both ways. I left it alone. So then I treated it as a +4. So +4, in other words, I dealt with the stuff behind the minus and left the minus as is for right now. and I'm going to deal with it later. Just make sure you do one or the other and don't try to do both. Don't treat it as a -4 and also leave it as a minus. One way or another. So -6 minus 12 is -18. If I want to add or subtract vectors, I just add or subtract their components. So I add or subtract the horizontal and I add or subtract the vertical. 15 minus -16 is 31. And that's my answer. Okay. We can also add or subtract things vertically. I'm sorry, vertically, visually. If I had, let's see, the vector u -2, 5 might look something like this. Okay, and the vector v 3, -4 might look something like this. That's not the best representation at all. Let's try and get a little bit more accurate. Let me see if I can grab some graph paper. Okay, so I've got my graph paper, and I basically just wanted to show you how you can do this visually as well. And sometimes you'll be asked to. So let's go ahead and start sort of in the middle of the graph paper. And remember that u is -2, 5. Okay, so I'm going to start, let's see. I'm going to start actually down here. -2, 5. So if this is the starting point for u, I'm going to go 2 to the left, and then 1, 2, 3, 4, 5 up. So that would be the ending point. So there is u. Now, I'm told to do 3 u's, so I'm going to keep going. So 1, 2, 1, 2, 3, 4, 5. And the same thing again. Okay, so that's 3 u's. Then I want to subtract 4 v's. Okay, so that's the same as adding -4 or adding 4 negative v's. It's the same as -4 times v or adding the opposite of v 4 times. So what was v? V was 3, -4. But I want to do the opposite of that 4 times. So I'm going to take away 3, -4. So if I'm starting here, the opposite of 3, -4 would be -3, +4. And I want to do that 4 times. So I'm going to go -3, 1, 2, 3, 4. -3, 1, 2, 3, 4. I really thought I was doing this with enough room to spare, and I don't know that I have. -3, 1, 2, 3, 4, and I'm just going to make it. -3, 1, 2, 3, 4. So these are 4 opposites of v's, because v would have been +3 down 4. V would look like that. So I'm doing the opposite of v 4 times. All right, so it's hard to see this on my camera, but basically all of this together is left 18 and up 31. That's like the sum total of my efforts after doing 3 u's followed by 4 negative v's. And this is something you can do, and sometimes you're asked to do it visually. And you basically, you put them start to finish, pick up with the next vector, start to finish, next vector, start to finish. And then the total sum of that, if people ask you to draw one vector that does the whole thing, you start from the very beginning point and go all the way to the ending point. And that vector would be -18, 31. Sorry it doesn't fit the whole page. Or the whole thing doesn't fit on the page well. All right, last one I want to do is I want to use these same values and do one where I'm asked for instance, let's go with this. All right. Let's put a 2 in there so we have a scalar as well. So we've got a scalar, we've got a sum, and we've got a magnitude. We've got 3 things going on. So I'm asked to do 2w, which is 2 times 1, 2, plus v, which is 3, negative 4. And I'm going to go ahead and do that first. That's 2, 4, plus 3, negative 4. 2 plus 3 is 5. 4 plus negative 4 is 0. And I'm asked to actually find the magnitude of that. So really the whole thing was magnitude. Okay, the magnitude of that, remember it's kind of like Pythagorean Theorem. Horizontal component squared plus the vertical component squared. Square root of 5 squared is just, well, I started to write my answer there. 5. Okay, and now keep in mind, this can all be written as, it's exactly the same thing if I write it as the sum of unit vectors multiplied by scalars. I could leave it like that, and I could do 3, let's see, where is this? 2w, 2 times 1 plus 3, and get 5i. I just think it's a little bit easier to work with it in component form, and then put it back into unit vector form at the end if we needed to. So I hope this has helped you, and I appreciate your coming, and I'll see you in the next video.